discussion about I'm. And then we can all drink some wine. Have Zabi say something, and then we can drink some wine. I just want to comment on maybe a few of the open issues. If some people saw some of these slides in my talks the last few days, so I've also just thought maybe it would be. So I definitely don't have a whole lot more I want to say beyond what's been said. Is kind of nice on this point. I just want to step back to this original slide. I think this is just amazing. I mean, I commented this on this the other day, but I mean, I think the fact that we were able to get all of these different wavelengths in one event, sort of everybody getting their car. But I think we can also be a bit deceived by this event. If it had happened twice as far away, we probably wouldn't have detected the gamma rays. The X-rays would have been really hard to detect. Radio, we don't know because it's still brightening. Maybe we would have eventually seen it. The kilonova, we would have probably been able to find, although if it had been a bit further away, maybe this technique of searching all the galaxies, there would have been many more galaxies to search. So I think things are going to get harder, but these close events, this is like the Rosetta Stone for telling us about these mergers. And so I think we're going to use, this event is really going to represent a sort of gold-plated thing that we're going to be comparing things to, even as things get further away and a bit murkier to figure out what's going on. But I do want to comment. As people know, during this follow-up effort, there was an attempt to keep, however many thousands of astronomers from leaking this kind of thing to the public. And since Matt's here, I have to rib him a little bit. That he named his Hubble proposal very suggestively BNS merger. So there was a period of time, a few days after, where he went to the Hubble Space Telescope.
Did I defend myself? I did tell them to change the name.
You did?
The Hubble schedule.
That's their fault. Okay. So NBC 4993, what are we looking at? The BNS merger. So I had to get a screenshot of this. As we discussed, I think the exciting thing for me ahead is that we can argue about which channel we went through with this binary. But the exciting thing is there are going to be other channels. And as we've talked about, the outcome of the system is sensitive to two things: the maximum mass of a neutron star and the total mass of the binary. And while one is going to be the same, whatever the maximum mass is, the mass of the binary will change, and so we're going to get a whole menu of different things. I think, for arguments we've discussed, that this thing did go through a hypermassive neutron star phase to get the massive outflows and accretion disks that we maybe inferred from the kilonova. Like Ben said, I don't think we have very good evidence that it produced a long-lived stable remnant. But maybe the next binary will have a much lower mass and will produce something qualitatively different. I'll come back to that. Or maybe it will have a very high mass and the electromagnetic signal will be much wimpier. In fact, we know about some short-duration gamma ray bursts. I remember the first one, 050509b, which was localized in 2005 outside of an elliptical galaxy. Wen-Fei Fong pointed out, and I think was also pointed out in another paper, maybe it was Ben Gompert's paper, that we can actually rule out for that GRB a optical counterpart at early times, which would be as bright as the blue kilonova we saw from this event. So we at least know that some short GRBs, which presumably observe fairly face-on, don't produce this very bright kilonova vision. And that event also was a fairly wimpy GRB, which could mean we were off the jet axis, or it could mean that maybe it did a prompt collapse, this bottom channel, and we got a fairly weak outflow of material and also a weak accretion disk, which gave us a wimpy GRB. I think qualitatively, the other thing we're going to be looking for in the next few years with advanced LIGO are mergers between black holes and neutron stars. And it hasn't been discussed much at this conference, but if the neutron star if the black hole is not too massive, you can tidally disrupt the neutron star outside of the horizon. That can give you quite a large quantity of tidal ejecta, so we'll get a very fast-moving, powerful red kilonova, but maybe a wimpier blue kilonova because we don't have the dynamical ejecta where the neutron stars collide. But maybe we'll still see something. So I think this is what's very exciting to me, is to think about what's going on ahead. I just want to make one comment about the short GRB. This wasn't said explicitly, but most of what we know about short gamma ray bursts is based on the fraction that have redshifts, and of those, or fraction that have X-ray afterglows, and of those we only get redshifts for about 30%. But based on that population, you can create a luminosity function and a rate of short GRBs, and that rate's about 10 per gigaparsec cube per year, the observed one. You can squabble a little bit about that number. Now we have a rate of binary neutron star mergers, and you can see that that's roughly 100 times greater. So the two options are that only a tiny fraction of neutron star mergers make observable gamma ray bursts at cosmological distances, or more likely, the things we see at cosmological distances are beamed into a fairly tight solid angle. So if you assume that all the neutron star mergers are the source of GRBs, or all neutron star mergers make the GRBs we observe, then it does give you some constraint on the typical half-opening angle of the GRB jet. And that's typically about a tenth of a radian. And I think for this event, the evidence is indeed that we're seeing it outside of that typical half-opening angle, which is giving rise to a lot of this interesting phenomenology. I'm not going to say much about the short gamma ray burst. It's already been said. I do think one of the open questions we should think about is what is the explanation for this delay. As Andrew said, it takes a bit of time for the jet to break out of the ejecta shell, the blue kilonova material. Is that what the reason is? If it were really the time for a black hole to form, I mean, several seconds, that's actually quite a long time, I think, for a lifetime of the object compared to what we're seeing from the kilonova. So I would favor that the black hole formed earlier. And so if this delay, I'm really pushed towards some picture where the delay is due to the ejecta shell. So we should think about, what are the constraints on it? Maybe that will tell us something interesting. But anyways, I think this delay is very fascinating. It'll be interesting to see if that's ubiquitous or if it varies. I mean, it'll be interesting to see if we have different mass binaries. Maybe the ones where the black hole forms faster, we'll see this is delayed by less time, and that will tell us something. So that would be very cool. I mean, I think we already discussed that, we have evidence possibly for this more powerful outflow off of our line of sight in terms of this, orphan afterglow, which initially is beamed out of Chandra's line of sight, but then as it slows down, interacting with the ISM, it enters the line of sight. And Raphael discussed the off-axis afterglow models, which I think, fairly natural explanation. I think the cocoon is also a possibility, but I am struck by the fact that this is what you'd expect to see if we had a short GRB pointed in another direction. With the properties that we infer for the cosmological one, we just put it 20 degrees off axis and we get this for free. In fact, I remember before this was detected, we were all sort of saying, keep looking in the X-rays, we're maybe going to see it brightening, because we were just waiting for this in the week. So this was pretty natural when this was seen, and Greg discussed the radio, which is also very exciting. And whether or not this turns over and falls down, maybe more consistent with the orphan afterglow. If it keeps brightening, then we clearly have a lot of mass getting high velocity, or maybe more consistent with the cocoon. Kilonova stuff. We've talked about the different. I don't want to dwell on the different components of the ejecta. We've talked about the dynamical matter, the disk wind ejecta. I do think, I've worked on this for a while, I do think these disk outflows are a very promising source to get a lot of material. Point 1c is, as Daniel said, we actually find this matter comes out a bit slower, so that's maybe a bit in tension with the IR spectra that Ryan discussed. On the other hand, as he was mentioning, this is sort of the velocity that he was modeling with Kaysen's models is actually the sort of the kinetic energy weighted velocity, which may actually be this high for a disk wind. So we may actually, maybe what we're seeing, not so much the slower matter. So I don't know. I think that this is a reasonable explanation for the red kilonova. So I was thinking about kilonova for a long time before we were calling them that, and it was partially motivated. I was a graduate student at Berkeley. I shared an office with Dan Trilly. I remember the burst that was localized to Andromeda. I think he was the first person who said, "Look, this is overlapping with Andromeda," the one that Zuzа mentioned earlier. I think he had put it up on our wall. And so I really benefited from my discussion with observational astronomers. And this was a gamma ray burst that he detected in 2008. And it was a short GRB. It had some extended X-ray emission, which we still don't understand the origin of. And then it just completely dropped out in the X-rays. And it wasn't actually detected initially in the optical. And then over the next few days, we saw this brightening and fading in the optical. So, this idea of Liam-Paczynski's mini supernova was around at this point, but we didn't have any basically the original Liam-Paczynski model left the radioactive heating as a free parameter. And so we didn't actually know how bright the Liam-Paczynski mini supernova should be at this time. And this was, very frustrating, but we did try to fit this thing, I remember, to just a nickel 56 model at that time, so we didn't know what else to do, not with much success. And and the other problem with this was we tried to find the host galaxy of this thing, and we couldn't find it. So we couldn't actually tell, the absolute distance, and since we didn't have a physical model for what this kilonova-like thing was, we couldn't place it at a distance that way. And so this was sort of our first hints of these type of phenomena, but we didn't have any real proof. And so it was actually this observation that really got me thinking, okay, we got to figure out how bright these things are. So it's actually driven by this observation to actually calculate the radioactive heating, and that's what we did in 2010. I remember I didn't know how to do this myself, so I was calling around talking to nuclear physicists. Eventually got in touch with Gabriel Martinez-Pinedo and Almudena Arcones at Darmstadt University in Germany. Various people told me were the people to calculate this. The trajectories we used, the R-process ejections that we used, were all the way available back, in the late 90s. This is from some of Rosbach's simulation. But no one had thought, well, maybe we should just figure out what the radioactive heating is at these late times so that we can normalize these models. So that's what we did, and figured out this brightness scale, which ended up being about 1,000 times brighter than the nova. It's true that we assumed iron opacity, but before us, people had done even worse. They'd assumed electron scattering, which was completely wrong. So we were moving towards the right direction with these models. But nevertheless, after this, I think I've already said this to many people, but after this event happened, I thought it would be entertaining just to take the bolometric light curves coming off of our dark energy camera, HST, etc., and plot them over this original model for a kilonova, and we got this excellent agreement, even though this is a bit of a cheat since we assumed 100% thermalization efficiency in this early model. We were assuming the wrong capacities, but to me this was very striking. Convinced me that we were basically seeing what we discussed before. But as we've talked about, the devils in the details and in the complicated color evolution, which is Ryan. I just want to emphasize this point again. It was emphasized once, but it isn't just a photometric argument that we have these two components. If you look at our optical spectra and our infrared spectra at, say 2.5 days, there's clearly an optical peak and a separate one in the infrared. So I think it's pretty clear we are seeing two independent components interacting. And as Jenny discussed, depending whether we get the blue or red depends on the exact elements that we have, whether we have silver or silver and gold. It's sort of the distinction I like to make. And it was even realized that, by various people that we should see both of these. In fact, red or blue is in the title of our paper in 2014. And it was basically because we expected the polar regions to be less neutron-rich than the equatorial regions. Our original idea is that it was all the equatorial polar regions were filled with disk winds. That was before the Japanese group started finding this blue, significant quantity of blue polar material from the colliding neutron stars. But we still don't totally know. The outflows from the disk, depending on the lifetime, could be red or blue. I think this is one of the important questions: is can we really get fast enough disk outflows to explain this early blue component we saw, or do we need these high dynamical ejecta masses which are pushing us towards really tiny neutron stars? I think that's one of the important questions for the modelers. And so again, this is just based on some visualization that Dan Kaysen did of what we think we saw. We think we saw this sort of blue plume followed by this sort of more spherical red ejecta cloud. And I didn't think anyone mentioned it, but there was actually some polarimetry done on the red kilonova component that may suggest it was more spherical. I don't know how constraining that is. Maybe Ryan can comment. So maybe maybe it's more consistent with this kind of accretion disk wind coming out spherically than some sort of equatorial thing. Again, as I said, I just mentioned this, but I think this is important for the modelers. Can we really get 10 to the minus 2 or more, even a few 10 to the minus 2 material when the neutron stars collide? This is the plot that Ben showed for Manning Gauss-Fine, where in principle, if we go down to 11 kilometers, we can get this much. But it was David was warning me that some of these equations of state are completely ridiculous or unphysical in terms of they're like polytropic equations of state or something we know are not correct. So I think this really warrants higher resolution simulations of the colliding neutron stars, much better neutrino transport. Easy for me to say, but
and radiation.
And radiation. Yeah, neutrinos, radiation, heating. Yes, we need to do it all. Also, we need to worry about neutrino oscillations. There wasn't too much discussion, there was a little discussion about undoubtedly stuff, but there's a lot of physics that goes into this blue stuff coming out. That it's telling us a lot, but we have to deconvolve this a lot. Red ejecta. I think this was mentioned, but I think we are having some evidence that this neutron star was not surviving forever. If it survived forever, it would just blast this whole thing with neutrinos. We would have an entirely blue cloud coming out, I think. But this is quantitative. I forget somebody, maybe Glennis asked about the exact lifetime we need to get the red stuff versus the blue stuff. This is the YE distribution of the ejecta, where we put in a central neutron star of some variable lifetime before it collapses to a black hole with the accretion torus, and we look at what comes out. And if the lifetime is very short, you get all red stuff. If the lifetime becomes longer than about 100 milliseconds, you get all blue stuff. We need to improve upon these calculations. These were with an alpha viscosity and a very simple neutrino transport. We need to do more. I don't think this was explicitly mentioned, but I don't know if anyone went through the numbers, so I'll do it again quickly. To explain the abundances of the R process elements on the Earth, the average production rate in the galaxy over the time up to that point is roughly this amount of R process material per year. We now have a rate of binary neutron stars from LIGO, which we can convert to an equivalent Milky Way merger rate. And if we combine those, we can conclude that whatever the site of the, if neutron star mergers are the dominant site of the R process in our own galaxy, they need to produce at least this much material. This is very crude, but it's roughly the few 10 to the minus 2 to a few 10 to the minus 3, depending on whether you think it's around the high or the low end. From this event, we think we inferred a few 10 to the minus 2. So, at least naively, it seems like we have enough of this being produced. We should have had enough produced in our galaxy to get the R process. But, again, we need more events. Maybe we are on the low merger rate, and maybe we're not entirely convinced that we've made the heaviest element. So there's a lot of work left to do here, but I think this is, Jim was right, I think it's the simplest explanation. So this is the figure from, the summary figure from my little quick review on this. I don't have a whole lot more to say. I just want to say that I was struck by the fact that I felt this was a fairly well-behaved merger. Everything that we saw was either seen before in some form or predicted. Now, you could argue whether or not we'd expect to see a gamma reverse slightly off axis. People have claimed to have predicted that. But definitely, we were waiting for the GRB off axis afterglow to brighten, and then on cue it sort of brightened. So to me, I think this is a real triumph for all of our work in theoretical astrophysics. I just want to spend the last 2 minutes talking about, as we go ahead, we expect to detect binary neutron stars when LIGO reaches advanced sensitivity. Pessimists will say it's 7 per year. Optimists say it could be up to 100 or per year, I think. That's what the range would correspond to once LIGO can see these to 200 megaparsecs. So we're going to see these things from different angles. We're going to see them for different combinations of masses coming in, so it's nice to think about what type of diversity we might see. So one thing, as was already discussed, is the fact that it may be that the blue material is coming out in the polar region, and we have this very high opacity equatorial or more spherical outflow. Definitely we're going to have some tidal material in this plane. So it's conceivable that if we view an event in the equatorial plane that some of this blue material, at least some of it, will be blocked. I don't know if it will be as complete as shown here, because if the blue stuff is indeed expanding fast, even if we're looking in the equator, we should see some of it peeking out. But this will tell us a lot. If we see an otherwise similar event from a different angle, it will teach us something. Rafaela showed a plot like this. This is, I don't think she emphasized this point of her plot, but there's a slight bias to detect binary neutron stars face on because the gravitational waves are stronger, a slight convex bias. So this is the detection probability below some observing angle, so it's like a cumulative distribution. And so then this is the, this was the 68% range of inclination angles when you use the Hubble constants, if you believe that either Reese or Planck is right. It may have changed a bit since the final version, but that's roughly where we could have been with this event, maybe a little to the left. This wasn't that uncommon. I mean, if you look, you know, if we saw it from a small viewing angle, it's sort of a 10% chance. If we saw it from the large end, it's, you know, sort of 50% chance. Okay, so it's not like we got extremely lucky per se. If we see it, if it really is 20 degrees, we did get pretty lucky. But we're going to see a fair fraction of these, both in sort of where we would be able to test the red and the blue and the red kilonova model. But like I said, I wouldn't count on there not being some blue emission, even for the larger inclination angles, if it's expanding fast enough. But that will teach us something about how fast the blue stuff is expanding. We can also expect that if we see less massive binaries, that they will give rise to longer-lived hypermassive neutron stars or even supermassive neutron stars, and that should turn more of the disk wind ejected blue. So we should look for, in the future, for correlations between the inverse correlations between the binary mass and the blue and red points. Yes.
These curves are for see which angle.
This is
So
okay.
as you show that if I see it from
Yeah, so these were for disk outflows from Kaysen and all. So this was based on Rodrigo and I simulations from 2014. And
so assuming that you see everything from
this is assuming you would see everything.
Okay.
Yeah, so there will be inclination effects, and then for a face-on merger, we should expect to see some kind of correlation like this. But this assumes that the blue stuff is coming from the accretion disk. If the blue stuff is dominated by the collision, you know, maybe it will be more ubiquitous. But I think there's a general expectation that the lower mass thing should produce more neutrinos and bluer stuff. In some sense, we have to go up. And then I think Ben discussed the real wild card in all this is we don't know. This event, I think, did collapse to a black hole fairly quickly, but maybe we're going to have a tail of very low mass binaries that maybe don't, that maybe survive for quite a while. And I think it's quite likely that they will be magnetars, meaning they'll have at least small scale fields that are very strong. And they will definitely be rapidly spinning, so you know, this should inject a lot of energy into the environment, or at least should do something qualitatively different than the other ones. So I wouldn't be surprised if, maybe it's a small fraction, but whatever the low max tail of this distribution does, it could do something radically different. I'm not going to say something too specific about that. But this is just some simulations that we did with Nicola Bucciantini in 2012, where we had an ejected cloud and we put a magnetar in the middle, pumping, rotate. It's kind of like a miniature pulsar wave nebula. It's pumping in rotational energy. And if the magnetar is not, the spin down luminosity is not too high, the ejecta is sufficient to collimate that magnetar into a jet, and this could possibly explain some of the extended emission we see after some short gamma ray bursts that we don't understand. If the magnetar is even more powerful, it can possibly even, you're basically inflating a bubble of hot plasma behind the ejecta shell. You induce Rayleigh-Taylor instabilities, and you can sort of blow the whole thing apart. So it may even be a more isotropic, high energy signal. Some of this will be reprocessed, make a brighter optical signal. I expect everything to be brighter. All right, and then the final thing, very last thing, is, nobody talked about this, but this is something that I think we should think about more. We did hear about the Hubble constant, but I think it's important to note that this kilonova was bright enough that 17th magnitude at 40 megaparsecs. When these things are being routinely discovered at 200 megaparsecs, hopefully 2 or 3, maybe 4 years, even the smaller telescope, 2-meter telescope ZTF and Black Gem could detect these things. In fact, Black Gem, I think, is actually exclusively detected to doing this type of follow-up. So you basically have a factory for learning stuff about LIGO sources. At design sensitivity, a fraction of mergers will be even further away, and those could be detected at this luminosity by a dark energy camera. So you can imagine we're going to get a lot more of these further away, where maybe the uncertainties due to proper motion, peculiar velocities, are smaller than they were for this one. And so, one thing is to try to relieve the Hubble constant tension. I think that's interesting, but I think looking further ahead, if these, if we had a source at a few gigaparsecs of this brightness, it could even be detected by LSST with some kind of TLO observation. Now, we're not going to detect neutron stars that far with advanced LIGO, but if we think black hole neutron stars produce something qualitatively similar, assuming the black hole isn't too massive and it's spinning, etc., those you can see to a distance which might be 2 to 3 times further than the neutron stars. And furthermore, advanced LIGO is hoping to upgrade its sensitivity by a factor of 2 in maybe the next decade or 5 years. It's planned for LIGO A+, I don't know if you can tell me. So anyways, it's possible we could detect these things out at distances that would be interesting for doing other cosmology eventually. Whether it's competitive or not, I think we need to do a detailed study, but at least now we know the rates of these are fairly high and they do produce fairly bright optical signals. So I basically want to conclude at this point. I've already showed this to several people, but since there's a few new people here, we had a workshop in August where we made predictions of what the first EMGW counterpart would be. Rodrigo Fernandez said jetted GRB, so he actually wins. But there were several of us that talked about these ideas of blue kilonova. And most of us also got wrong when the first detection would be. Most of us, nobody said 2017, and somebody said 2018, but most of us were thinking. So this event was just a present that came a bit early, I think. And I'll finish there. Thanks.